How's it going, guys? Vincent here, and in this video I'm going to be talking about mechanical ventilation. And with the current coronavirus outbreak and the number of patients who have acute respiratory distress syndrome, or ARDS, there is a huge demand for mechanical ventilators. And right now people are wondering, why don't we have more mechanical ventilators? And the reason is that before this pandemic happened, hospitals didn't need to have that many ventilators because it just didn't happen that often. We didn't have people who were in critical enough condition that would need it, so hospitals focused their resources on other places where they could save lives. So right now there's now a huge demand for mechanical ventilators, and we've had a lot of companies jump in and claim that, oh, they can start providing ventilators really easily. And the issue that we're running into is that mechanical ventilation is extremely complicated, and there are a lot of feedback loops, and there's a lot of engineering involved in order to help us get to a solution that is going to actually save lives and not just hurt people. And so what I'm going to be doing in this video is talking about mechanical ventilators, how they work, and also, what are the challenges that we're currently running into in order to make more of these things. And so the goal at the high level of ventilation is to promote the exchange of gas inside of your lungs, because the issue is that if we take a patient who currently has coronavirus, their lungs have filled up with liquid, and specifically this is their alveoli, and because of this there's more distance in between the actual capillaries and the gases, so there's more resistance to gas or mass transfer. So you're trying to get oxygen into your blood, you're trying to get carbon dioxide out of the blood, and as we get these liquids building up inside of all these little balloons, your alveoli, the issue is that there's more resistance to mass transfer. People become hypoxic. That's a fancy way of saying that their oxygen is now low, so their cells aren't getting the oxygen they need, so they can't do cellular respiration. Consequently, they start, having organ failure and stuff like that. So very, very bad. And the issue is that, as you have your diaphragm, which is this muscle at the base of your torso that's kind of like going up and down, that's the thing that's naturally making you breathe right now. The issue is that as you increase all this resistance to having this gas transfer in your lungs, your diaphragm, which is only so strong, can't really handle it anymore. And so that's where, literally your diaphragm needs energy to be able to operate. And because it's so hard to actually get oxygen in, it can't get that energy that it needs to operate. And so you're going to start experiencing all these failures. These are extremely severe cases, and people are on the brink of death. So the goal of the mechanical ventilator is to basically jump in and provide that energy that you need to push air into your lungs to get that gas transfer to actually happen. And so, at the high level, yes, we're trying to get a lot of gas into your lungs and a lot of gas out of your lungs to help you when you need it, because you physically cannot do this on your own. And so what they do when you're on a mechanical ventilator is they stick something called an endotracheal tube, an ETT, down into your airway. And at the end of this tube is a little balloon that will inflate, and it inflates to create this seal. So you've got a good seal so you can start having the ventilator do its job of actually putting gases in, taking gases out. And then once it's doing this, we have a lot of set points and rules that have to begin to take into account. So, naturally we breathe about 12 times a minute. So once every 5 seconds, we expect an inhale and an exhale. And so, with these ventilators, they have this self-triggering mode where if they recognize that someone has just tried to inhale, if they sense that little drop in pressure, then the ventilators will trigger and they will, activate a breath. They will push in a defined amount of air. Generally, this is 500 to 600 milliliters of volume. So this is a 1 liter beaker, or bottle, and so 500 to 600 is about half the volume of this. So when that ventilator goes down, it's going to push down from the 600 point down to the 0 point on this bottle. And so once that happens, it recognizes this triggering event. The issue is, though, that when we're dealing with patients who are in critical condition, not everyone is always going to be having that natural trying to inhale breath. And so when that happens, we have these other set points that are running in the background to recognize, if I haven't triggered a breath in over 5 seconds, I'm going to automatically and default to having a breath go right now. The other thing here is that because patients are in different conditions, they're going to need different amounts of pressure to help us force in that volume of air. Because you've got a lot of liquid building up in your alveoli, we're going to need to work to varying degrees of difficulty to get that finite or specified volume of air into your lungs. And so with the mode called assist control, which is what's used in these mechanical ventilators, the goal is that we've already told the system push in 500 to 600 milliliters of air, depending on the size of this patient. So bigger people are going to need more oxygen, or heavier people are going to need more oxygen also. So, once we've defined all these set points and we have this system set up, we can have this ventilator kind of take over and do its job of making this all happen. And so if I haven't detected that a patient has tried to breathe in over 5 seconds, I'm going to trigger a breath anyways, just to make sure that we're getting gas in and gas out so that we can continue to have oxygen and carbon dioxide transfer in the lungs. And so, that's one of the big hurdles here is like, it's not just a simple little pump. It's a pump that has a lot of other machinery around it to detect what needs to happen and when it needs to happen. And so, and also depending on the resistance, how hard does this pump have to work? You need a pump that can handle different resistances and be able to change to very minute or precision in order to make these things happen. So with the assist control also, the issue is that your lungs have this thing called compliance. And so as your lungs get to a certain degree of compliance, which is where, if your lungs are full of liquid and it's very difficult to change the volume of your lung to actually get that gas in, your lungs are said to be not very compliant. So that pump is going to have a high pressure in order to push that air in. And so one of the issues that we ran into in the early days of our mechanical ventilators is that it is so much more complicated than just a simple, let's do a high pressure, then a low pressure, then a high pressure, then a low pressure, because the issue is that as your alveoli, which are balloons essentially inside of your lungs, as we go to high pressure, then to low pressure, then to high pressure, then to low pressure, we're shearing the tissues. And so the issue with this is that as we shear these tissues, we're creating even more inflammation, which creates even more resistance. And so it's not as simple as just, let's just do this high pressure thing and let's leave it at that. What we did to overcome that issue that, we've learned along the way is like, we'll keep the pressure relatively high the whole time to basically keep all of your balloons, your alveoli inside of your lungs wide open. And then we would just go with smaller volumes of gas that it's not having to change quite as much, which prevents the amount of shearing that we would be doing otherwise, which helps us reduce the amount of inflammation and keep your alveoli intact. Because previously we would be collapsing the alveoli as we're trying to push oxygen into the lungs. And this would make things even worse for us and result in us killing even more people than we should have. We're trying to save people's lives, not hurt them even more. So, we learned our lessons. We are understanding the set points and the kinds of ways that we want to handle all these devices. And so to me, this is very good to know because it means that our medicine and science is learning from its mistakes. We've got a lot of stuff going for us right now where we need it most. And we've got a lot of engineers and scientists and physicians and doctors and nurses and lab technicians who are all working very, very hard around the clock to scale up as many of these devices as we can get in order to save people's lives. It is very challenging stuff, but we've got really smart people working on it. So we're doing our best that we can with what we have. And I hope this video is helpful for you guys. Please let me know if you have any questions. Thank you all for watching. Please stay safe and wash your hands, and I'll talk to you next time.